Okay, so first question, how was quiz 0?
I looked at it. I have not gotten to it yet. I was going to ask you. I wasn't sure what it's to do.
Yeah, it's for you,
Okay.
So you do it, and again, do it like it's a real quiz, but then the solutions are there and they should more than explain any question you have on the matter.
Mhm.
So, yeah, buddy. So, yeah, do that. And then quiz 0.1 is the same kind of thing. And it's just so we can make sure that we're all on the same page. I was recording the solutions yesterday and would have posted them yesterday, but my phone got full and I didn't realize I'd been talking for like 30 minutes and then I checked and it only recorded the first 45 seconds of what I said. And then I ran out of time, I had to do stuff. And so it's not posted yet. It'll get posted hopefully later today or whatever. But yeah, let's say those two quizzes by Monday at your leisure. And again, they're both they're really review and everything, but just have them done, I guess by Monday would be good so that we could keep moving along. Okay, so any questions before we begin? Because we got a lot to do today.
No questions.
Okay. Good to go. So let's do just a little bit of review of what we did last time. If you remember, we had our secret code or our special function that took A to a number, it took B to a number, it took C to a number. What we're going to work with today, just briefly to kind of just get back in that headspace, is we're gonna say we're only worried about the letters A, B, and C. Those are the only letters we're gonna worry about. So then our domain is going to be the set of letters A, B, and C. And like I said last time, we didn't need to map it to 1, 2, and 3. I could have picked any numbers at all, 7, 3, and let's just say 4, right? And we said, okay, is this thing a function? Well, yeah, it's defined for some domain. So there's a domain of input values. And there's a rule that takes each input value to one and only one output value. And so by definition, this is a function. And then of course, we call this the domain. And then the set of outputs that we get when we plug in the entire domain, we call that thing the range. Those are my output values. We call that the range. Okay, now just a couple things just to note is there's no reason I needed to organize it like this. I could have said, I could have organized it like this. I could have said, okay, B gets mapped to 7, A gets mapped to 3, C gets mapped to 4, and we'd see this thing is still a function. We have a domain. Every one input goes to one and only one output. All the outputs we call the range. Okay, that's good. We also saw that if we get tricky here and we say, well, what if I wanted to map A to 7? I wanted to map B to 7. We said, well, that's still a function by definition because we have a domain. We have a rule that takes every one element of the domain to one and only one element of the range. And it's like, well, what about this guy? Well, he's fine. B gets mapped to him. That's cool. B doesn't get mapped to 2 things. He just gets mapped to 1 thing. A gets mapped to 1 thing. So that's cool. A range is a little bit different now because nobody hits 3, right? None of these arrows come and hit 3. That is, 3 is not an output of this guy. So that kind of changes the range a little bit. But nonetheless, still a function. Now, though, the problem is if we wanted to get our message back, right? Like I wrote you a message that said 7, 4. Well, what did I mean? Did I say AC or did I say BC? And that's kind of the question, right? It's like, well, and what we're getting at here is that the inverse, if you remember, we talked about an inverse, which is what we just computed, right? You have an output, and we want to say, well, where did that output come from? So if 7 is the output, and I have 7, now I'm asking, well, what does it go back to? And we could see that if we consider the inverse as a function, well then this isn't a function because it doesn't obey the rule. This one input would map back to 2 different outputs. And so we kind of have a problem there, right? And that's really illustrated by, what did my message say? Did you say A or did you say B? So we have a problem with that. So that's kind of what we were talking about last time. We introduced some notation for that. Now, I want to kind of stop for a second and go down a little bit of a rabbit trail, because we're going to be, a lot of your questions are going to involve, I'm going to give you a function, I'm going to give you a formula for a function, and I'm going to say, what's the domain of this function? And for instance, one thing that's going to show up a lot is if I say f of x is, oh, I don't know, how about 1 divided by x, we'd say, well, there's a value that, there's one value that you cannot put in there. What value is that? What value can you never divide by?
0.
0, right? And you hear that a lot. We can't divide by 0. You may have heard it's undefined, right? And that's a problem. And so we'd say, so when we're trying to figure out the domain of this, we have to say, well, we can't put 0 in. And so 0 is not one of the possible input values, and so on and so forth. So I want to give you an idea of why that's the case first. So, because I didn't hear this until I was like a junior as a mathematics major at UW. And this is the first time I heard why we can't do this. I heard, a couple wishy-washy, well, this and that, but this is why. And I think it's important to go over this. Okay, so first off, get this out of the way here. First off, division isn't the thing. It's kind of a made-up thing. And what do I mean by that? Well, the way that things are defined in mathematics, usually one thing is derived from another thing. So let's do this example. Let's say I have a function, and I'm going to call it multiply by 5. It's a function. It takes any input value x, takes whatever your input is, and guess what it does? Guess what it does? It multiplies it by 5, right? So, okay, let's work with this function. I'm gonna abbreviate this function to make notation simpler. I'm just gonna call it MB5 of x. And it's exactly what I said. You take whatever your input value is, multiply it by 5, and that's your new output. So let's do a couple values. Multiply by 5 of 1 would be, well, wherever I see an x, I just replace it with that number right there. So I take 5 times 1 and I get out a 5. Multiply by 5 of 2 is 5 times 2, and that's 10. We'll do a couple more. Multiply by 5 of, let's go -3. It'll be a little tricky here. Multiply by 5 is -3. That's the same thing as 5 times the number -3, which comes out to -15. Now, first off, is this a function? It's the question, right? We have a domain, apparently all real numbers. I can't think of any number that you can't take and multiply by 5. Even 0 works, right? You could take, it is possible to take 5 times 0. That's perfectly fine. You go 5 times 0 is 0. 5 times any number is fine. So my possible input values, right? The domain would be all real numbers. In fact, all complex numbers, but we're not going to go there right now. We could take any number and multiply it by 5. That's fine. So the domain is all real numbers. Okay, so it has a domain. And now for any one input, how many outputs do we get? Well, I plug in a 2. There's only one number that comes out, right? It's only the number 10 comes out. So I guess we get one output. That's the same for any possible number. Okay, now remember how this example I have right there, this way satisfied the definition of a function, but this way doesn't, because we had an example of one thing that maps back to 2 different things. Well, that's not the case here, right? I could take any output number. I could say, so now we're thinking about finding the inverse, right? We have some output of this function multiplied by 5, and we want to know what was the input. So trying to find the input, we took something and multiplied it by 5, not sure what it is, but let's say we got out a 35. What number must that be?
7.
7, right? And so in symbols now, we could say, okay, you took a number, put it into this, and you got out a 35. So then the inverse, if you remember, this is what we use for inverse. We have the name of the function. We put a little -1 up there and say that is going back in that direction. We're taking an output, making it a new input. And we'd say, well, then this thing came from the number 7. But what did you do in your head? You said, well, 35 divided by 5 is 7, right? So in other words, the inverse, you take any output, you know where that output came from. What you did was you took 5 times x and got an output y. So what you just did in your head is you said, oh, that's the output. What I'm going to do is just divide it by 5, and I'll get my original input back. And so, okay, that's the same thing as y divided by 5. In other words, whatever your output is, you take it and divide it by 5. But of course, it's not really defined yet. It's like this is, we've seen behind the veil. We know where this is going. We already know how to divide by 5. But with mathematicians, that's not how they set it up. They say, well, you know what? We need a function that's going to undo multiply by 5. And so they say, well, first, what is the inverse operation? Well, the inverse operation would look something like this, right? We have this guy going forward, he gives us outputs, and now if we take any one of those outputs, we'll get an input. We'll find the original input. But the question is, and this is the key here, is just like before, we have a perfectly good function going forward, and we need to make sure that when we go backwards, we don't get anything that maps to more than one possible input. And I could see, like, yeah, this is fine. Any one output you put in there, you're only going to go back to where you came from, right? Like if I say, take 15 was my output, I'm sorry, -15 was my output, there's only one number that will work as the original input, and that's -3. Ditto with 10. If I start with 10, or if 10 was my output, I know that there's only one number in the world that's going to work there, and that's the number 2. And so, yeah, we could see that this is also for any one input to the inverse, we get that it came from only one output. So we could say this thing is indeed a function. So we're going to give it a new name, and we call it, instead of multiply by 5, we call it divide by 5. And we say whatever input you have, you take it and you divide it by 5, right? Like, but that's what it means. That's kind of like we're defining. We're saying when you do this, what this means is the inverse of this function right there. Any questions so far?
No.
Okay, cool. Pretty straightforward. Okay. So that's how we define, that's how mathematicians define division. They say it's the inverse of multiplication. So let's make a new function. Multiply by 0 of x is you take any number x and you multiply it by 0. I'm going to abbreviate it MB0 of x equals 0 times x. Now let's put in a couple values. I'm going to say multiply by 0 of 1 means I take 0 times 1, and what do I get?
0.
Okay, so I have multiplied by 0 of 3, and I get 0 times 3, and what do I get?
0.
Okay, maybe we'll try one more and see if anything changes. Multiply by 0 of 5 equals 0 times 5 is, that's still 0. So now when I go to play the inverse game, right, I want to see, well, what's the inverse of this? So I do the same kind of thing. I say, okay, you put some number into multiply by 0, and you got out a 0. So what original number did you start off with? Well, yikes. And you can see what happens if you want to think visually what's going on is if we took like all the numbers, positive 1 and 2, and we have an output, possible outputs, it's like saying, okay, you multiply 2 by negative 2 by 0, it goes to 0. Negative 1 by 0 goes to 0. 0 goes to 0. 1 goes to 0. And so it's like, oh man, we're in a bad way here, right? Like if this was bad, if you have two numbers going to 1 and trying to get back, you might be able to fix that. Like, and we're going to see that in a minute. If you have a little bit of crossover, sometimes it's okay because in the context, you could say, well, in this context, I know I didn't give you A, so it must have come from B. But in this case, there is no possible way of undoing this I'm going to call it a traffic wreck, right? It's like a car crash that everything's going into 0. And so you say, well, then where did it come from? It could have been any of the numbers. It could have been any of them, negative 2, negative 1, 0. It could have been any real number. So there's like no way of undoing this. And so we could say, if we're trying to define this function, we can't do it. And so we just say, you know what? We're going to leave it undefined. Therefore, the inverse of multiply by 0, in other words, divide by 0, is undefined. That's what it means by being undefined. Now you've seen it. Now, now the veil has been lifted and you've been initiated into the wider world of mathematics. Can I erase this stuff?
Yes, you may.
Okay, that made sense?
Yes.
Okay, cool. So it's kind of cool because we're already talking about this type of idea, like, okay, we have a function, it maps things to other things, and we could talk about getting our inputs back, right? And that's the idea of an inverse function. And that leads really nicely into why can't we divide by 0? Well, because it's hard to define. You can't just say, well, if your input was negative, it came from this. Or if your input was positive, then it was this. It's like there's no possible way to undo that. So we're just going to say we can't define it. We're done, undefined, leave it. So, okay, now I noticed in your book that they gave another way of relating these things together. They gave ordered pairs, right? And so this is just another way we could define this function right here, right? this function going from A, B, and C to 7, well, I guess just 7 and 4, they said that we're going to have ordered pairs of inputs here and outputs here. And so in this case, to define this function, I would say, okay, when the input is A, the output is 7. When the input is B, the output is also 7. And when the input is C, the output is 4. And they say this defines a function. And indeed it does. It's just we're saying the exact same thing with this as we're saying with this. The notation is just a little bit different. What can be confusing though is that this notation right here, say 1, 2, we're also going to use that to define an interval. That's all in quiz 0, and we go way, way, way into it. And so there might be, you might think that it could be ambiguous. Am I talking about the ordered pair where this is an input value X and that's an output value Y? Or am I talking about the interval on the number line from 1 up to 2, not including the endpoints? Well, if it's ambiguous, I will be sure to let you know. I will say this is the point or the ordered pair 1, 2. If it's an interval, I will refer to it as the interval 1, 2. It should not be a problem. I don't want to try to shield you from that because it's coming right around the bend. Like this is just the way it is. We use this to describe points and we use it to describe ordered pairs. We use it to describe relations. We use it to describe intervals, and it comes from context, which one it means. I don't want to try to water it down. That's just the way it is. This isn't me. This is like the way all math is. So we're gonna do it. It should not be a problem. Just wanted to mention that because I know your book gives you a bunch of problems like this, and in quiz 0.1, there are a few problems like that. And it should not be a problem. So I didn't bother to ask if you had written that down, but I guess it's too late. So sorry. All right. Okay. One more thing before we actually get into talking about some examples of functions and what we're going to be working with functions. I'm going to define 2 functions. And at first it's like, I'm going to be like, whoa, wait, what, wait, but it's not so bad. And so here's the definition. This is how it is. They'll give you, like I said, you get a definition and you're like, what does this even mean? Then it starts to make some sense. This is what we're going to do. Definition. Given any function, given any function f, we define a new function. I'm going to call it the function dom. Yes, we're calling it dom. Dom of f. We're going to write it like that. This is the thing you will want to remember, dom of f. Define the function dom of f to take a function as an input and return that function's domain as the output. Remember how I said functions don't need to have, we don't want to think about functions as being something you put a number into and get a number out of. That's going to mess us up because this is so much, this will be nice for us in the future. This is a function which takes a function as an input and returns that function's domain. So this function I've defined here, f, okay, going this way. Let's forget about these black lines going backwards for right now. This function right here is that those ordered pairs. A goes to 7, B goes to 7, C goes to 4. Well, it's pretty clear that the domain here is the set A, comma, B, comma, C. And we would say, well, that is DOM F, the domain of F. Nothing tricky going on, right? It makes sense. Like, in other words, all this does is I'm just saying, what's the domain of F? And so it takes a function as an input and returns its domain. Similarly, we are going to define the function ran of F. Guess what that one gives you? When you plug in a function, what does ran give you?
Range.
A range, right? So it's the same thing. To take a function f, we'll say take a function as input and return its range as an output. We're not going to make a big deal out of this. I'm not going to like quiz you on this or anything. This isn't going to show up on an exam, except if I just say, what's DOM F? That way I don't, it's again, mathematicians being lazy. Instead of writing WHATSTHEDOMAINOF, what is the domain of F? I could just write what's DOM F or what's ran F. And so let's see, given this function right here, F as defined, you tell me what is ran F?
7 and 4.
7 and 4. The set of the outputs, 7 and 4. Okay. Now, we're going to now, and I'm sorry, we're going to tweak our definitions one more time for domain and range, because now we're going into the world of real numbers. The functions that we talk about from now on are going to take real numbered inputs, except for these guys. But the functions that we talk about from now on are going to take real numbers as inputs and return real numbers almost always as outputs. And so, since that's the case, now that we're in this context of real numbers going in, real numbers coming out, it's going to help us a lot to refine our definitions. Can I erase these two definitions here?
Yes.
Okay. We're going to refine our definitions of range and domain. And I should have left that right there. Given any function f, we will define the domain. The domain of f to be, this is, if you could get this in your head, this will help you a lot. All allowable inputs to f. Like I said, I kind of hinted at an example. If I say that the function f of x is defined as 1 over x, you already told me that we cannot put in the number 0. That's what I mean by allowable inputs. We cannot allow that we put a 0 into here. that does not make sense. Okay, and so we're going to say, well, then all other allowable inputs would be everything except for 0, and that would be the domain. Okay, so all allowable inputs. This is, I'm just boiling stuff down. If you can remember this right there, then pretty much every question you're going to get for the next 5 or 6 years doing math, that is the way you want to think about the domain, is the allowable inputs. And of course, we're talking about, well, okay, moving on. We're going to say, again, given any function f, we will define the range of f to be. This is how I like to say it. What you get out of f, what you get out of f when you plug in the entire domain of f. Okay. So in this case, the way that we have defined f over here as with a, b, and c and 7 and 4, clearly the domain, this is pretty obvious that I can't put in a d. That's not allowed because I haven't even defined it, right? I can't say what's f of d. Well, the way that I've written this right now, D is not defined. I haven't said what to do with D, so it's not an allowable input. Similarly with 1 over x, I can't allow that we put in a 0. So, okay, so then we see to find the range. What we're going to do is imagine that we've taken all of the input values. We've taken all of the allowable inputs to f, and then we plug it in. And we see basically, and another way of saying this is what gets hit. That's why I love the arrow notation, because it's like, well, A, if you shot an arrow from A, it would hit 7. If you shot an arrow from B, it would hit 7. If you shot an arrow from C, it would hit 4. So what gets hit? In fact, that's going to be, I'm going to say that a lot. What gets, and you'll see when we actually start graphing functions, this makes a lot of sense to say it this way. What gets hit when you plug in the entire domain? Okay, any questions thus far?
No, I don't think so.
Nope. Okay, cool. So, all right, I'm going to go ahead and erase all this. And now we're going to actually get down to the bread and butter of what we're talking about in this class. So after looking at the homework that you've had up until now, I've seen that you have been given formulas. Something, oh, I don't know, maybe like this. We'll say f of x is equal to, how about 2x plus 1? Something like that. Now this thing is a function because it's a rule, right, which takes inputs and gives you different outputs. In fact, it tells you how to get an output. That's your rule right there. Given any input x, you take x, multiply it by 2, and then you add 1, right? You're familiar with order of operations, right? We don't need to go over that.
Yeah.
Right? Okay.
Yeah.
So, you know, when I see that, I know, okay, first we got to take x and multiply it by 2, then we add 1, and then we get whatever the output is, right? And so what we like to do is then graph this type of thing. I'm a big fan of graphing. I used to hate it. Like when I was taking Algebra 2, it was my most hated thing. And I was like, if I never graph anything again, I'll be happy. But it turns out that it's going to, like I said, I'm lazy and I'm all about being as lazy as possible. It turns out to be less work to graph stuff. So we're gonna really get into graphing in our class. So what we do usually, and this should just be review. And again, we'll be reviewing for another maybe couple days. What we do is we say, okay, we're going to imagine that this line is the real number line. It goes from negative infinity up to infinity and includes all real numbers in it. And then we're going to say, all right, this, and in fact, right, it doesn't matter that I used x. I could have used t. I could have said f of t is equal to 2t plus 1 or whatever. But I happen to use x. But in every case, it doesn't matter what letter I use. This is always the input axis right there. So we think about, okay, you give me any x, that x is right here, and we plug it in. Now what do we get out? We think about this as the y-axis, but it doesn't need to be y, right? I could say, well, then we'll think about these as y's. I could have said, let's think about these as f's. We could label this the f-axis. I don't care what you call this axis. You could call it f, you could call it y, you could label it with a little smiley face for all I care. This one, though, does matter. If there's an x input right there, we had better call this guy x. But again, in every case, this axis is always the output axis. Okay, so we're just going to calculate a couple of points. What happens? Let's say I want to plug in the number 1. And again, I'm putting that on the input axis. So I'm asking, okay, we're taking the number 1. What happens to number 1? Tell me, what is the output?
3.
3, right? Symbolically, we could say, okay, f of 3, when 3 is my input, I just say, okay, when 3 goes in, I replace, since I put a 3 there, everywhere that I see an x, I just simply replace it. Oh, sorry. The input is 1, but this is what I asked you, right? When the input is 1, I replace the x with a 1, and you're right, you said, okay, 2 times 1 is 2, plus 1 is 3. So 3 is my output. In other words, f of 1 is 3. And remember, last time I said that this symbol represents the output you get. So if I were to plot this point right here, we would say, okay, yes, it's 3 because we could actually calculate it. But symbolically, right, we could also write that as f of 1 right there. I kind of like that because it shows you the relationship, right? It's like, where did this number come from? Oh, it came from 1. It's right there. Nice. We'll do a couple more. What happens when I plug in a 2? What do we get?
5.
Yeah, because 2 times 2 is 4 plus 1 is 5. And so we get a 5 right there. We say the height is 5. Plugged in a 2. We could also call that f of 2 because it represents the same thing, right? It's like when I plug in the 2, what does that mean? Well, it means this right here. And that right there, we could think about that as, yes, the number 5, but it also equals f of 2. So we're going to use, sometimes it'll be beneficial to think about it symbolically. Sometimes we'll want the actual value. I'm just writing it up there so that we could have this in mind. And we go on and on and on. Let's just do one more. What happens when I plug in 0? What do I get out?
1.
1, right? The 0 kills that thing. Plugging in 0 is one of the nicest things you could do in a function. It's one of the easiest things because it usually makes a lot of stuff disappear, right? We get rid of everywhere that we see an X just kind of disappears. All we're left with then is the 1. And so I will plot that 1 right here. I'm going to say that value is 1, which is also f of 0. We can think about it that way. And this turns out to be, and I'm sure you've seen this before, the equation of a line, right? And if we went through and evaluated all of the points here, right? If I said, well, there's something in between 1 and 2, and if I were to plug that in, it would come out right here. If I plugged in this value, it would come out. Now, let's just stop for a second and consider 2 questions. What is the domain of F for this F that I've written?
All real numbers?
All real numbers, exactly. Because I'm thinking back to our definition, all allowable inputs, and I look at that and I think, okay, can I multiply a number by 2? Yeah. Is there any restrictions on that? No, I could take any number, right? I could take 0, multiply it by 2. I could take any number smaller than 0, multiply it by 2. Bigger than 0, yeah, okay. Then can I take whatever that is and add 1? Yeah, no problems there. So we're going to say all real numbers. And on quiz 0, you see, this is how we're going to be writing real numbers. That's the set of real numbers. It's just a fancy way of saying all the numbers from -2 and blah, 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 all the way to everywhere, right? So that's the set of real numbers. Okay, then what's the range of F? Any ideas?
Well, it can't it can't be all real numbers because it doesn't pass through 0, right?
Now this is, I'm so glad you said that. So let's think about this. And this is one reason why how graphing goes along with what gets hit by. And this is why I like to think about it like that. So remember we said that the range is what you get out whenever you plug in the entire domain. And so we're imagining that we're plugging in all of these numbers. And we could see that, say, when I plug in a 1, this is what I mean by what gets hit by. It's like saying 1 gets mapped to 3. So we shot an arrow from 1 and it hit 3, right? We shot an arrow from 2 and it hits 5, right? And so if we shoot an arrow from 1/2, 3/2, it's going to hit this number right there. When we shoot an arrow from 0, it hits right here. Shoot an arrow from here. And so this is the thing, and I kind of see what you're saying. It's like, well, the range are these points right here. But remember that the arrow isn't landing out here. This is just a fancy way of telling me that when the input is 2, the output is 5. I want to, real quick, let's think about if we were doing this as arrows. And I can't write all of the real numbers, but I could do something like this. 1, 2. We know that 0 gets mapped to 1. We know that 1 gets mapped to 3. We know that 2 gets mapped to 5. 1 get -1. I guess we get mapped to -1. -2 would be -3. And so now you could see what's happening here, right? Like when we take these numbers right here, if I wanted to make this finer and add a 1/2 in between it, well, this would get finer too, right? Since 1 is getting mapped to 3, 0 is getting mapped to 1, 1/2 is going to get mapped to something between 1 and 3. It's going to land right there. Something between 1/2 and 0, like 1/4, again, that's going to get mapped to something there. And so this is kind of the idea I have in my head when I hear, or when we say we're plugging in all of the input values and seeing what gets hit by the output values. And so what I'm seeing right now is when I plug in all the positive real numbers, each one of those should hit something from here and up. All of those numbers are going to get hit, right? So those are my inputs. Those guys are my outputs right there. So everything from 1, when I actually plug in 0, I get out of 1. All of those guys are going to be hit. Now, what happens when I plug in, say, -1/2? What gets hit? Let's just calculate it. I'm going to plug in -1/2 right there. And I get, oh, well, actually, that does it. How about -1/4? I plug in f equals -1/4, or f of -1/4. I get 2 times -1/4 plus 1. What does that simplify to? Well, let's see. That's the same as -2/4 plus 1. -2/4 is the same as -1/2 plus 1. Well, that's 1 minus 1/2. That's just 1/2. Okay. So I plug in -1/4. And what gets hit? Well, it tells me to go here, and then the output value gets hit. It's right there. So that is 1/2 does get hit. And so, yeah, we're going to get, remember over here, when we plugged in the positive real numbers, we got all of these guys right there. Now it's like, well, is there a big gap? Are we not going to hit 0 or whatever? Well, it looks like we're closing in the gap. I plug in -1/4. And it looks like I'm climbing my way down. I plug in -1/4 and I get 1/2. If I keep doing that, just visually here, and this is what I love about graphing, I can see that, yeah, if you take a number in between here, between -1/4 and 0, plug that in, you'll get that number here. Get something closer, you'll get that number there. Eventually, you'll get all of those numbers there. And similarly, as I start going that way, plug in this number as an input, you get that number as an output. Plug in this number as an input, you get that number as an output. And as we keep going, finally, we get this number right here. And we should get 0 as an output. Let's just see. And I think I already gave it away what number that is, but let's say we want to define if 0 is an output. Because this is one of the things that you just said, right? You're like, well, I don't think 0 is an output. Like, I don't think when I plug in the real numbers, 0 shouldn't be an output because that's not touching 0. But let's just see. We're saying we want to know, is 0 an output of f of x? In other words, what do I need to plug in for x in order to get out a 0? In other words, with this rule, what number do I need to plug in for x to get out a 0? So I'm trying to solve this equation. Now I could say, okay, X gets multiplied by 2, then we add 1. So I'm going to get X by itself by first subtracting off 1. Oops. So I get minus 1 equals 2X. Divide both sides by 2. And that gives me 2's cancel. I get negative 1/2 is equal to X. And so it should be the case that when I plug in negative 1/2, I should get out a 0. Let's just double check. Plug in a negative 1/2 into that function. It says take 2, multiply by negative 1/2, then add 1. So I'm going to do that. 2 times negative 1/2 is the same thing as negative 2/2 plus 1. Negative 2/2 is negative 1 plus 1. Indeed, does give me 0 as an output. So we could see then, okay, when your input is negative 1/2, then 0 is your output. And similarly, right now, okay, so we've gotten everything from apparently infinity, right? Because the bigger numbers I plug in, the bigger the outputs are going to be, right? Plug in a 100, and we get 2 times 100 is 200 plus 1 is 101. Plug in 1,000,000, okay, then you get 2,000,001, and we could see that any output that we could want that's bigger than 0, there's an input for that. There is a number I could plug in to get that out. Going on this side, so we've got them all the way down to 0. Now we could start asking, can I get numbers less than 0? Yeah, if I'm over here, maybe let's say at negative 1, when I plug that in, the output, in other words, what gets hit, I love that idea of arrows. This just kind of tells you, this line right here tells you how to direct your arrows, right? When negative 1 is the input, it says to go down to here and then hit your arrow there. And if we wanted to know exactly where that was, I could just plug in a negative 1. Say f of negative 1 is 2 times negative 1 plus 1. 2 times negative 1 is minus 2 plus 1 is negative 1. And so we can see, yeah, plug in a negative 1, you get out a negative 1. Go further down, and it's going to tell you to hit this number right there. Further down, it's going to tell you to hit this number right there. So what I could see, the picture that's starting to develop in my head is like, if I take all of the input values, the entire domain, which we've already said, I've erased it, but the domain of f is all real numbers. There's no restrictions. All numbers are allowable to plug in there. If I do that, I could just kind of see by this picture and kind of drawing my arrows, because that's how I like to think about it. 2 goes in, 5 pops out. 1 goes in, 3 pops out. And I can see just by this picture, and it's kind of like, yeah, there's any height, right? Any output, because we think about the vertical axis as the output. Any height that you could imagine, 0, 20, negative 5, well, there is an input that corresponds to that right there. And so, what's the range of f?
All real numbers?
All real numbers. Every real number that you can imagine will get hit by it. And let's just real quick, because this is a good exercise to do. Let's say I didn't believe you. Let's say I said, you'll never get negative 15. There's no possible way you'll get negative 15. We could say, well, let's see if that's true. If we can't, then it should be impossible to say that negative 15 is an output of f of x. Well, that should then, in other words, it should be impossible that 2x plus 1 is equal to negative 15. Minus 1 from both sides, we get negative 16. I'm so glad I chose an odd number to start with. That's nice. And I could say, okay, divide both sides by 2. X. Negative 8. And I'd say, no, there is a value. You said that we would never get negative 15 as an output, but I just found that when you plug in negative 8, my rule tells me to go down here, and the output is going to be negative 15. So yes, indeed, you're absolutely right. The range of f is all real numbers. Now, real quick, yeah, it'll be worth it to go over this. So can I erase this right now?
Yes,
Good.
you can.
Okay. So now we also have graphs. Right now we've started graphing. So in the same way, I wrote like a column of letters and then drew arrows to a column of numbers and said, this defines a relationship. That relationship is what we call a function. I said we could do that with ordered pairs, saying one's the input, the next one's the output. The next ordered pair, one's the input, next is the output. You can also do it with a formula and say, given any input, do this to it, and that will give you your output. We could do the same thing with a graph. And I could say, okay, if this is my graph, like this, this will be a familiar picture. We will see this so much in this class, this type of picture. Yeah. Where X's are my inputs. And it's now what this has just done is I have now, maybe not explicitly, but I have defined a relationship between inputs and outputs. And we'll call this that. And I'm going to get rid of this because that is not the function of your graphing right now. In fact, I haven't even decided what this is. But let's say that this output here is 1. And maybe I give us a couple other points. Maybe I say something like it's 2, the output is 5. Ditto over here at -2. Okay, so I've given a couple points. I haven't defined the whole function. I could, if I wanted to, I could define it with a formula. But let's just look right now. And I'm going to say this right here. It goes on forever. And the way I've drawn this is that it will go, this line or curve is going to continue in this direction forever. In other words, eventually it will get to any X value in the future. And it will also get to any Y value you could imagine up in that direction. Same thing over here. Okay, it's going to go on forever in that direction. So any negative number you imagine, eventually this will get so far over that the negative number will jump up and touch that guy. So right now I've defined a function. It's not very explicit. We can't do much with it besides the 3 points that I've given us. But we're going to call it f of x. Now, just by what I've just said, can you take a guess what the domain of f is?
Well,
remember, this is going to go out forever in this direction. And this is going to go out forever in this direction.
so all real numbers?
All real numbers. And it's because now it would be different if I drew it going straight up, right? Or if I said it's only defined from here to here, then that would be a different thing. But just this picture, and right now we're just going to be thinking in terms of pictures, is that the domain of this guy would be all real numbers because I have defined for any input on the x-axis, because I said it goes forever in this direction, there will be an output, or that we can use this as a rule. So for instance, this rule says that when I plug in a 2, what gets hit? Well, this says we go from 2 and positive 5 gets hit. In other words, this means that f of 2 is equal to positive 5. Okay, then what's f of negative 2? When I plug in the negative 2 here, what is my output?
5.
Also 5, right? And that's, I've drawn it with a little point, meaning like, yes, these things are all together. This means that when I plug in a negative 2, what gets hit is that number right there. So yes, f of negative 2 is also positive 5. Okay, now, when I plug in a 0, what is my output?
1.
1, yes. Weird one. You don't really see the arrow on that case, but I mean, you could just say, yeah, it goes straight up and hits right there. Okay. Now let's take any number in between here and just see visually what happens. If I take a number right here and I plug it into my function, what gets hit? Well, it's some number here. And so it has to be bigger than 1, less than 5, but some number in there. And now I can just kind of ask, are all of these points going to get hit by some input? What do you think?
Yes.
Yeah, because I can, and now I'm just kind of visually, I'm doing the inverse operation here. It's like, well, suppose an arrow hit this right here. Where could it have come from? Well, is there a value? Yeah, actually, yeah, there is a value. If you started right here, you could have said, okay, if I plug this number in the same way we did here, we plugged in a 2, got out a 5. Here we're saying whatever number this is, if you plug it in, it will give you this guy. Just so happens, there's another number on the other side that if you plug it in, you get the same output. Interesting. What about all the numbers above 5? If we take any one of those, is there an input that hits that one?
Yes.
Yeah, and I could see that, right? I could say, well, if you go right here, if you had started right here at this number, call it Z, and you plugged it into Z, we would see, plugged it into F, you would see that, yeah, this number right here, F of Z, whatever it happens to be, would get hit. And since I told you that this thing goes on in that direction forever, I could see that that's going to be the case forever and ever. And in fact, we're going to get all of these numbers forever and ever. They will be outputs for some input. Again, now what I'm doing is I'm trying to evaluate what's the range. And I'm thinking, wait, range is defined by domain, at least the way we've done it. So what's the domain? Well, as I've drawn this picture, you've already said that the domain is all real numbers. There is a rule which says for any real number, I don't care how far this way, I don't care how far that way, I don't care if it's 0, that there is a rule which tells you what the output is. Okay. So when I do that, now we're trying to find what is the range of F. When I do that, when I plug in all real numbers, what numbers are hit?
All numbers above 1.
All numbers above 1. Yeah. What about 1 itself? Is 1 itself one of those numbers?
Yeah.
Yeah, that's the way I drew it, right? I started off by saying, yeah, it's going to hit 1. 1 is one of the numbers that does get hit. And then just by looking at the picture, I could see, well, pick any number along there. Is there one that, oh yeah, there's one that comes from that. In fact, you can use 2 of them there too. Okay, so we're going to say all numbers bigger than 1 or including 1 in quiz 0 in painful detail. This is given. You will know for certain that that is this interval right there from 1 up to infinity and including 1 right there. So we could say, because remember, what does range mean? It means it takes a function as an input and gives you out its domain. Its domain, when we're talking from now on, we're talking about sets of real numbers. This is a set of real numbers. There's that. We are out of time for today, but I do want to show one more thing here. Now, in this case, we've already said this thing is a function. So, and we didn't really go through it, but we said, but I just kind of went along that, yes, this thing is a function. Why is that? Well, one, we have a domain. We have a rule that relates inputs and outputs. Well, what was that other thing? For any one input, how many outputs must we have?
One.
One and only one, right? And so is that the case here? I don't know. Let's just take any one input and we'll see how many outputs does it generate. I will take this one input and it tells me to go to here. And so therefore that is the output. Are there any other? Nope, that's it. That's the only output for that one input. And similarly, anywhere I go along here, I can see that that's the case. Have you heard of the vertical line test?
Yes.
Right? This curve passes the vertical line test. If I drew, let's do this, a vertical line, right? Right there. If I drew a vertical line, if it touches once, what does that mean? Well, it means that when I plug in this number, it touches one time, meaning that there's only one assignment for that guy. That would not be the case if I drew something like this. Right? In that case, you'd say, well, hold up. When I plug in a number here, this says that I get this number as an output, and it says that I get this number as an output. One input goes to two outputs, so it would not be a function. It would fail the vertical line test. Saying the same thing, right? If it fails the vertical line test, that means that there is an input, at least one input, where when you plug it in, you get more than one output. That is not the case for this guy. This guy is good to go. For any one input, we get one and only one output. I don't care how far out here you're going. I don't care how far out here you're going. If I look straight up, a line would touch once, which means that there's only one output for it. Is the inverse of this a function?
No.
No. Why?
Because each input would have two outputs.
Yes, exactly, right? Because we're saying, okay, remember the inverse is the inverse relationship. We're saying you got some number as an output. Where did it come from? Well, it's kind of like when we had this, right? A, B, C, we had 7, and we had two different things, both mapping to 7. We have the same thing here. It's like, well, if that is your output, 7, there's two possibilities. It either came from here, this number, which we'll call, well, let's call it A and B, this number B, or it could have come from this number here, which we'll call A. And so while the forward, or the F that I've drawn right here is a function, because for any one of these, we get one output, we could see that there are outputs that came from more than one input. So the inverse is not a function. Okay, I think we're good for today. I went over 11 minutes, which actually for me that's pretty good.
That's pretty good.
So, any questions as of right now?
No questions.
Okay. Let's see. We did not get as far as I hope we get, but I'm not surprised about that. So, okay, definitely. In fact, I would like it if you completed quiz 0 by Friday. Quiz 0.1. Don't worry about that until after our class Friday. It would be cool by Monday, but we'll see where we are on Friday, and then we'll see if that'll be due on Monday. And again, it's not due. I'm not grading it, but it's this is for you, and there's plenty of materials. Any confusion that you have while you're taking it should be taken care of in the solution videos.
Okay.
If it's not, of course, get with me and we'll talk about it. I think that's it. So unless there's anything else.
Thank you.
Yeah, you're welcome. Good seeing you again.
Nice to see you. Bye-bye.
All right, bye.